Okay, so let us begin with today's lecture. So we will continue with counting where we left off in the last lecture, and we were discussing circular arrangements. So we you imagine that you put n objects, n different objects on a circle, around a circle like guests at a dinner table, and you want to know how many ways are there in order to arrange them. And we notice that there is an important difference between circular arrangement and arrangement on a line, that is a linear arrangement, which is that the rotation doesn't matter. So all that matters is only the relative position of the various objects. So for example, in a linear arrangement of n distinct objects, the total number of arrangements is n factorial. However, for circular arrangement, if these same n different objects are arranged around a circle, we noticed that every circular arrangement, if you fix this particular position, so for example, if you fix this particular position, then and start counting from here clockwise, then you have 1, 2, 3, and you could have 3, 1, 2, and then you could have and then you could also have 2, 3, 1, and so these are, if you start from the person sitting here or the object sitting here and enumerate the rest of the circular arrangement clockwise, you get a linear arrangement. But notice that the corresponding linear arrangement would be 1, 2, 3 for this one, 3, 1, 2 for the next one, and 2, 3, 1 for the third one. So these are different linear arrangements, but the circular arrangement is the same because these three are merely clockwise rotations of the same circular arrangement. So the point is that the same circular arrangement leads to 3 different linear arrangements if there are 3 objects in total. So if there are total n objects, then the same circular arrangement of the n different objects will lead to n linear arrangements. So if there are n objects in circular arrangement, then one circular arrangement of n objects leads to n linear arrangements of the same objects. So if the total number of linear arrangements was n factorial, then the total number of circular arrangements would be n factorial divided by n, because every circular arrangement leads to n different linear arrangements. Okay? In other words, this is n minus 1 factorial. So let us continue today with further examples of circular arrangements. So the next example is the number of ways without removing any empty seat, so that 9 guests can be seated at a round table with exactly 10 seats. So you notice that when you are doing counting problems, the identity so there are 9 different guests around a table and one chair is vacant. But so the vacant chair of course doesn't contain a human being, but for the purpose of counting, you can imagine that a vacant chair just represents a 10th guest, right? So it's exactly as if you were sitting 10 guests around a round table, and the total number of ways is 10 minus 1 factorial, because the total number of ways of sitting n guests was n minus 1 factorial, and this is 9 factorial. Okay? Any questions? Okay. So the next example is the following. So so in the previous, so first we considered the number of ways of seating 10 guests at the table. Then we went on to consider the number of ways of seating 9 guests and 1 empty chair. So now we are going one step further. We now have 10 possible seats around a circular table, but there are only 8 guests. So now there are 8 chairs. Now when there was then so there are now 8 guests, so 8 filled chairs and 2 vacant chairs. Now when there was only 1 vacant chair, we got by easily because we could treat a vacant chair just as an additional guest. Okay? So this we cannot do now because of the following reason, that if you treated the two, if the 2 vacant chairs were actually 2 different guests, then of course having a vacant chair here, oops. So let's put it in this way. So if you had a guest here, let's call it guest 1, and you had a guest here. So if these 2 spots were occupied by guest 1 and guest 2, then there could be 2 different arrangements, because guest 1 could sit here and guest 2 could sit there, or guest 2 could sit here and guest 1 could sit here, right? Okay? But if you had vacant chairs, then these 2 chairs being vacant doesn't lead to 2 different arrangements, because you do not really need to permute the 2 vacant chairs between them. Okay? So things are getting complicated. So that's the message. So, but first let us assume that we had 2 distinct guests, 2 different guests for the 2 vacant chairs anyway. So then we could sort of argue as before and declare that the total number of seating arrangements is 10 minus 1 factorial, which is 9 factorial. However, we now have to go back and correct for the fact that the 2 different vacant chairs are not, in fact, they do not represent, they cannot be counted as 2 different guests. Okay? So how do we do that? So as I already drew in the previous slide, so if you consider the 2 vacant chairs as 2 different guests or 2 different ghosts, then the arrangement of a vacant chair here and a vacant chair there would lead to 2 different seating arrangements. Okay? The existence of a vacant chair here and a vacant chair there would lead to 2 different seating arrangements if the vacant chairs were counted as 2 different guests or 2 different ghosts. Okay? However, in reality, they are not different, because a vacant here and a vacant there is just represents 1 arrangement of the guests. So in other words, every arrangement of 8 guests and 2 vacant chairs gives rise to 2 different arrangements if they were distinct guests. Okay? So when you counted the total number of ways of arranging the 8 guests and 2 vacant chairs by thinking of the 2 vacant chairs as 2 different guests, then you overcounted, you represented every real arrangement of 8 guests and 2 vacant chairs by a multiple of 2, by a factor of 2, because every actual arrangement of 8 guests and 2 vacant chairs gives rise to 2 different arrangements of 8 guests and 2 ghosts. Okay? So this 9 factorial, in other words, overcounts the true number of arrangements of 8 guests and 2 vacant chairs by a factor of 2. So you, for getting the actual real number of arrangements of 8 guests around a round table of 10 chairs, you should divide this 9 factorial by 2, and get the answer as 181440. Okay. Any questions? Okay. Let us continue with combinations. So, many counting problems involve the counting the number of subsets in a finite set satisfying certain conditions. So, for instance, if you have a group of 8 persons and you want to form 5% committees out of it, then how many such committees can you form? And this is a general, and this can be generalized in a simple manner. Given n different objects, how many ways can you choose k of them? So, the previous bullet point is just a special case of this with n equal to 8 and k equal to 5. Okay. So, the key point here is that the order in which the people are picked does not matter, because if you have a 5% committee, how you list the names of the people in the committee does not matter. You just want to have this particular committee consisting of these specific 5 people. Okay. So, here is the result. So, let C and K denote the number of ways of choosing k objects from n different objects. So, then C and K is you can write down a formula for C and K, which is n factorial divided by k factorial times n minus k factorial. Okay. So, imagine that so to understand why this should be the case, we imagine that we arrange k objects out of n objects on a row and we count the number of ways using 2 different methods. So, the first use is to use the multiplication principle directly. So, you just want to place k objects out of n total objects. So, this is k and you have a total pack of n. So, this is k and this is n, and you want to arrange these k objects in a row. So, how do you do that? Well, the first you think of the positions as placeholders. So, you number them 1, 2, 3, 4 up to k. So, the first position can be filled in n ways. For every way of doing that, the second position can be filled in n minus 1 ways. For every way of filling the first 2 positions, the third position can be filled in n minus 3 ways, up to the kth position being filled in n minus k plus 1 ways, which is exactly n factorial over n minus k factorial, for which we used the notation p and k in the previous lecture. Okay. So, this is what we had. But now, let us count the same thing, that is the number of ways of arranging, ordering k objects out of n different objects in a row. Okay. So, on one hand, that number is p and k, which is n factorial over n minus k factorial, which you already know, but we will now count it in a different way. So, let C and k, as we have already discussed, let C and k be the number of ways of choosing k objects out of n. Okay. So, if C and k is the number of ways of choosing k objects out of n, then I can do the following. So, let us get back to the task of arranging k different objects from n different objects in a row. Okay. So, we will accomplish this task in 2 steps. The first step is that first we will choose the k objects to be placed on the table. So, that you can do in C and k ways. Now, for each way of choosing the objects to be placed on the table, these could be arranged among each other on the table in a linear order in k factorial ways. Okay. So, the total number of ways of arranging or ordering k objects from n different objects on the table is C and k times k factorial. Okay. But we already know that the total number of ways of putting k objects, of ordering k objects, arranging k objects in order on a table from n objects is P and K, which is n factorial over k n minus k factorial. Okay. So, these two, the only conclusion is that these two numbers must be equal, because they are just two different ways of counting the same thing. Okay. Once we have that, we can write down, we can take the k factorial down on the other side and write and obtain that C and k is P and k over k factorial. And once we notice that P and k is n factorial over n minus k factorial, we notice that C and k is therefore n factorial over k factorial times n minus k factorial, okay, as in here. So, this is the main idea. Okay. And as again in counting problems, it is equally important to understand how we argue. So, all these arguments are very important, and not only the remembering of the formulas. Okay. So, any questions about C and K and its expression? Okay. So, what are other notations for C and K? So, well, you can play around with the location of the and the K, upstairs, downstairs, etc., and get some other notations for C and K, but these are all mere decorations that represent the same thing. And this number C and K is traditionally described or pronounced as n choose k. So, from now on we will call n factorial over k factorial times n minus k factorial to be n choose, and we will call it n choose k. And generally this particular notation is usually a very popular one, at least in math. Okay. So, here are some notational conventions. N choose 0 is taken to be 1, n choose n is also taken to be 1. And here is a simple fact, a warm up with the notation n choose k. So, we have n choose k is equal to n choose n minus k. Why is this the case? Because n choose k is the total number of ways of choosing k objects from n objects total. Now, when you choose k objects from n objects in total, you leave out n minus k objects. So, choosing these k objects out of n objects in total is exactly the same as choosing the n minus k objects which you left over. Because if you specified which objects you are leaving over, then equivalently you are specifying which objects you are selecting. So, what is the total number of ways of choosing n minus k objects out of n? It is n choose n minus k. Now, if you think of them as the left out ones, that is exactly the same as the number of ways of choosing k objects out of n, and that is n minus n, and that is n choose k. So, n choose k is the same as n choose n minus k. Okay, n choose k is equal to n choose n minus k. Any questions? So, let us continue. So, let us take a different, so n choose k, to motivate n choose k, we or C and k, we motivated it through the example of forming committees out of a group of persons. So, let us continue with the formation of committees, where we put various restrictions on the committees we can form, and that will lead to more delicate counting arguments. So, how many different subcommittees can we form from a 9-membered specified committee if the president and the vice president do not serve on the same subcommittee? Okay. So, there are 9 people in total, out of which there are 2 distinguished people who are the president and the vice president. So, P and VP. Okay. And the restriction, so you want to form subcommittees, so subsets of this 9-member set, with the restriction that P and VP cannot be in the same subset. So, you want to count the number of subsets of this big 9-member set, so that P and VP, these 2 elements do not belong to the, these 2 people do not belong to the same subset. Okay. So, what can you do? So, if P and VP belong to the same subcommittee, you cannot count that, you cannot have that. So what are the possibilities? So P is present, president is present, vice president is not present in your subcommittee. That is possible. It can be the case that the president is not present, but the vice president is present. That is also fine. It is also fine to not have both the vice president and the president. So neither the vice president is present nor the president is present. That is also allowed. The only thing that is disallowed is to have both the president and the vice president. Okay? So these are three different possibilities, and we will count the total number of subcommittees belonging to the three categories separately and then add them up. So let us first count the number of subcommittees containing the president but not the vice president. So how do we do that? So other than the president and the vice president, there are 7 ordinary members. Okay? So if you have the president, so you have to select 5 members in total. You already have the president, so you need 4 members remaining. You cannot have the vice president, so these 4 members you have to choose out of the 7 ordinary members. So you choose 4 out of 7 ordinary members to complete your subcommittee, and this is 7 choose 4 ways. Okay? Any questions? So let us now look at the number of committees which contains the vice president but not the president. So this is a different category, but if you think of it in terms of a counting problem, it is exactly similar to the first case. So you have one, you constrain yourself to have one of the 2 special people and not have the other special person, and then you choose the remaining 4 members from the 7 ordinary members. Okay? So this is again 7 choose 4, just like the previous case. And the third type is a different type. It does not contain the president or the vice president. So both the president is absent, the vice president is also absent. How many such subcommittees are there? Well, so if the president is absent and the vice president is absent, that means that you choose all the 5 members of your subcommittee from the 7 ordinary members. So that can be accomplished in 7 choose 5 ways. So the total number of ways of choosing 5-member subcommittees so that the president and the vice president are not present together is the sum of these 3 ways, which is 7 choose 4 plus 7 choose 4 plus 7 choose 5, and you can simplify it to 91. Okay? By the way, so if you want to calculate these things, these kind of expressions, let's say 7 choose 4 via calculator, what you should do is that you should not calculate 7 factorial and then 4 factorial and 3 factorial everything. Okay? So what you should do is the following. So first you cancel this with the 7 factorial and get 7 times 6 times 5. Okay? And then you calculate 3 factorial, so the smaller one, which is 6, and then you cancel that from above. Okay, so that is 35. So the point is that you do not, so you do some simplification before you plug it into the calculator. You should not try to calculate 7 factorial or 10 factorial. I mean, they could be very large. Okay. Any questions? Okay. So let us now go on to game of poker. The game of poker is a very popular card game, and in counting problems as well as in probability, which we will see in the coming weeks, card games are very important. So what is very important is to count the number of ways of choosing different configurations of cards from a deck of 52 cards. Okay? So the first thing that you need to know, and this, for example, I did not know this when I started as a college freshman, is that you need to understand, you need to have a rough idea of how a deck of cards looks like. Okay. So some of you might know, some of you might not. So let me just give a description of how a deck of cards looks like. So there are 4 suits. So total is 52 cards. There are 4 suits of 13 cards each. Okay. So these suits have these standard names: clubs, diamonds, spades, etc. So anyway, so each suit contains 13 cards, and these 13 cards have numbers. So you start with 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So since we started from 2, we have had 9 numbers so far. 2 to 10 is 9 counts. And then you have Jack, Queen, King, and Ace. So basically the 1 is not there because you have the Ace here. So Ace is the top. Okay. And somehow there is an ordering of importance among these. I mean, 2 is the least important somehow, and Queen and King, and then Ace is the most important. Anyway, so what is a poker hand? So a poker hand, so poker is the game that we will, in this particular module, we will be referring back to poker again and again. So let's talk about a poker hand. So what is a poker hand? A poker hand is a selection of 5 cards, any 5 cards from these 52 cards. So since we are doing counting, let's begin with how many ways are there of how many poker hands are there out of a deck of 52 cards. And of course, that's the same as the number of ways of choosing 5 cards out of 52 total. So that's 52 choose 5. Okay. And 52 choose 5 is 52 factorial over 5 factorial times 47 factorial. And as we already discussed, if you try to compute this directly, you will be in a soup. So what you do is that you cancel the 47 factorial with 52 factorial and get 52 times 51 times 50 times 49 times 48 divided by 5 factorial. So 1, 2, 3, 4, 5. So this is now more manageable, and you can plug it into a calculator and calculate it to be 2598 times 60. Okay. 52 factorial is beyond the reach of anything. Any questions? Okay. So the next question is, so the next counting assignment. So this is the first simplest counting assignment in poker, which is just to calculate the total number of poker hands. The next counting assignment is to calculate what is known as a royal flush. So what is a royal flush? So royal flush is to focus. So the royal flush is a poker hand. So it's a collection of 5 cards. It satisfies 2 conditions. So the first condition is that all the cards must come from the same suit. So either here, 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 or here. So the suit must be the same. And once you have the same suit, the 5 cards should be consecutive. And not only they should be consecutive, they should be the top 5 cards of that suit. Okay? So 10, Jack, King, Queen, King, and Ace. Okay? So that's 10, Jack, King, Queen, and Ace of the same suit. That's the particular poker hand is called royal flush. So here, once you choose the suit from which you pick your cards, you don't have any choice, because once you pick a suit, then you just need to pick the top 5 cards, the 10 through Ace of that particular suit. Okay? So the choice that is involved is just the choice of the suit. And there are 4 suits, so you just pick the suit in 4 possible ways. So the total number of royal flushes is as many as the number of different suits, which is 4. Okay? Any questions? Any questions? Okay. So let's now go to a little more complicated example. So this is a straight flush, but including royal flush. So here the cards are again from the same suit and they are consecutive, but it is just that they are not the top 5. Okay? So, they are not the top 5. So, this is excluding royal flush, but they otherwise satisfy the same conditions. So, the cards, so the 5 cards have to come from the same suit and they have to be consecutive in this ordering. Okay? So, how do you do that? So, again first pick the suit, okay, because they have to come from the same suit. So, first pick the suit. So, that you can do in 4 ways. Given once you know which suit you are picking from, then what you do is that you notice that for the straight flush you need to pick 5 consecutive cards from this suit. So, let us imagine that you have chosen this particular suit. So, you need to choose 5 consecutive cards from this suit. So, for specifying 5 consecutive cards, all that you need to specify is where you start from. Because once you know which card you start from, let us say 7, the next one will be 8, the next one will be 9, the next one will be 10 and the next one will be jack. So, once you know the starting card, you know everything else in your hand. Okay? So, once you have picked the suit, all that you need to specify is the starting card. And how many ways can you choose the starting card? Well, you have to pick 5. So, you cannot start later than 10, okay, because you have to have 4 cards later. 10 you cannot pick because you are because you are not a royal flush, then you just pick something from here, okay, and you start from there and fill out the rest. So, for each suit there are 9 straight flushes including the royal flush and determined by the lowest card. So, that gives you the total number of ways to be 4 times 9, which is 36. Okay? Any questions? Okay. So, 4 of a kind. So, what is 4 of a kind? So, there are 4 of the cards will have the same number. So, 4 of the cards, let us say, will be kings, and the 5th card will be something else. So, how many ways of doing that are there? There are 13 choices for the 4 cards with the same number, because if you choose, so first you choose the number of the card which is repeated. So, this you can choose as the ace, so the number to be repeated you can choose as the king as in the picture, or you could choose the ace, or you could choose the queen or jack or any of these 13 cards or any of these 13 numbers. So, once you choose the number of the card, so for this there are 13 choices because there are 13 possible numbers. So, once you choose the number of the card, there are 48 choices of the remaining card, because the 5th card has to come from a different number. So, once you choose the number, let us say king is your number. So, this you can do in 13 ways. For every, now fix that number. So, let's think of king, think of the situation where you have chosen the number of the card to be repeated 4 times. So, that is the king, let's say. So, then the other card has to come from any of the remaining cards. So, there are total 52 cards in total, out of which you have already selected 4 kings for your hand. So, there are 52 minus 4, that is 48 cards remaining, and you can pick any of those 48 cards. So, there are 13 choices for the first for the card to be repeated. Once you choose that number, you pick all 4 cards of that number, and then you pick any one card out of the remaining 48. So that's 13 times 48, which is 624. Okay. So here is another example. Full house. So what is a full house? So full house means that there are 3 cards of the same number and 2 cards of a different number. Okay. So again, we do it in the same way. So first we will deal with the 3 cards of the same number, and then we will deal with picking the 2 cards of a different but common number. So, wow. How do you choose 3 cards of the same number? So again, first you have to choose the number. So the number, the common number of the 3 cards, you can choose any of the 13 available numbers from 2 up to 10 and Jack, King, Queen and Ace, Queen and Ace. So this you can choose in 13 ways. For every choice of the number, you have 4 available suits. So suppose you have chosen, suppose your number which is going to be repeated 3 times is going to be king. So now there are 4 kings corresponding to the 4 suits, and you want to choose 3 of them. So in how many ways can you do it? You can do it in 4 choose 3 ways. So the total number of ways of picking the 3 cards that are going to be common is 13 times 4 choose 3, 13 for the number which is going to be repeated thrice, and 4 choose 3 for the card, for the 3 particular cards of that number, 3 suits of that number which are going to be chosen. Okay. So this gives you the 3 cards of the same number, but you still need to pick 2 cards, and these 2 more cards are going to satisfy the condition that they are going to be of the same number but not common to the number which has been repeated thrice. So you look at the numbers which haven't been repeated thrice. So there are 12 possibilities because one number has been repeated thrice. So there are 12 possibilities for the pair, and for each possibility, once you fix the number of the pair, let's say 7, then there are again 4 cards with the number 7 corresponding to the 4 different suits, and out of which you choose only 2. So you do that in 4 choose 2 ways. So what we did was that we had 3 cards of the same repeated number and then a pair of cards repeated 2 cards of a different number. We decoupled the problem. We first dealt with the 3 cards of the same number, and that gives you 52 possible choices. For each way of choosing these 3 cards having the same number, we looked at the possible ways of choosing the other 2 cards having a common number, which is 72, and so the total number of ways is 52 times 72, and this is 3744. Okay. So the next one is flush. So this is flush excluding royal and straight ones. So there are 4 suits. So flush just means that you have 5 cards, and these 5 cards do not. So these 5 cards just belong. These 5 cards just belong to the same suit. Okay, and you want to exclude the royal and the straight suits. So how do you do that? So there are 4 suits. For each suit, there are 13 choose 5 ways of picking 5 cards. So you just, without any restriction, you just choose the 5 cards. But you want to subtract away the sets of cards which are straight flushes or royal flushes. So these numbers we have already calculated before, and you sum the total number of royal flushes plus the total number of straight flushes and subtract them from 13 choose 5 and get 5108. Okay. So let me just continue with one slide more of poker, because we are in the mood for poker, and then we will take a break. So let's now think of a straight hand. So what is a straight hand? So a straight hand means that the numbers are consecutive, but we want to exclude the straight flush or the royal flush. So in straight flush or the royal flush, what happens is that the numbers are, so in straight flush, what happens is that the numbers are not only consecutive, they belong to the same suit. And in royal flush, what happens is that the numbers are not only consecutive, but they are the top 5 numbers belonging to that particular suit. So we want to, instead here, what we want to do is to count the number of straight hands, which are the number, which implies that the numbers have to be consecutive, but we want to exclude the royal flushes and the straight flushes. So again, since the numbers are consecutive, the most important thing to look at is the lowest number, because once you have the lowest number, then the other numbers will consecutively fall in line. If your lowest number is 10, then the next one has to be a jack, then the next one has to be a queen, the next one has to be a king, and the next one has to be an ace. Okay? So if you just look at the numbers, then the lowest number determines everything else. So the number for the lowest, we count the number of straight hands in the following way. So we first choose the numbers. Okay, so the numbers. So we first choose the numbers. So how do we choose the numbers? So the first or the lowest number can be obtained in 10 ways. And once you have the lowest number, the other ones fall in line because they have to be consecutive, because it's a straight hand. And once you have the numbers fixed, you can fill up all that remains to be done is to choose the suits. So you can choose the suit of this card in 4 ways, you can choose the suit of the next card in 4 ways, etc. So since there are 5 cards, you get the number of possible ways of choosing these numbers times the total number of ways of filling them up with suits. So 10 times 4 choose 4 to the 5 minus 10 times 4 to the 5. So that's without excluding royal and straight flush, because if you count in this way, you also, you can in fact get this combination in this manner, which can be a royal flush. So you have to subtract the number of royal and straight flushes, which you can obtain from the previous discussions. Okay. And finally, 3 of a kind. So what is 3 of a kind? So you have 3 cards of the same number, and then 2 cards of 2 other numbers. So again, you first consider the 3 cards which have the same number. So, and you fix the number. So this common number for the triplet of cards can be fixed in 13 ways, because there are 13 numbers. And for every number you have 4 cards. So out of these 4 cards, you can choose 3 cards in 4 choose 3 ways, because you need a triplet for that number. So 13 choices for the number, and then for each choice of the number, there are 4 choose 3 choices of suits. So 13 times 4 choose 3. So this gives you 13 times C4 3. 13 times 4 choose 3. And we need to pick the remaining 2 cards from the other 48 cards. So that number cannot be repeated. So, you forget the cards of the number which belong to the triplet. So, there are 48 other cards, and these 48 cards, from these 48 cards you can choose any of them for the first one, and for the next one you can choose any other card having a different number from the first card. So, that is 44, because once you choose 10, there are 4 cards having the number 10. So, you from the 48 you remove all the cards having the number 10, and you have 44 cards, and you choose any of those 44 cards for the first. And once you do that, you will notice that what you are interested in is really combinations of cards, whereas what you have counted is the ordered pair of the first card and the second card outside the triplet. So, you have overcounted, you have counted every combination of the first 2 cards twice. So, you have to divide by 2, and if you do the calculation, you will get 54912. Okay. Okay. So, this is a good point to take a break, and once we are back, we will continue with the binomial theorem. Okay, so let us continue with the lecture. So the next item after card games is the binomial theorem. So what is the binomial theorem? So the simpler versions of the binomial theorem you have already probably seen in high school. So the simplest example is the formula for expansion of a plus b whole square, and that we all know is a square plus 2ab plus b square. Similarly, you could do a plus b whole cubed, and that also some of us know is a cubed plus 3a square b plus 3ab square plus b cubed, and similarly you can continue with a plus b to the 4, etc. As we all know, so the main idea in the binomial theorem is the following. So if you considered a plus b whole to the power of n, we can kind of understand that we are going to have sums of, we are going to have linear combinations of terms like this. We are going to have linear combination of a to the highest power. So if it is a plus b to the n, it is going to be a to the power of n. We are going to have b to the power of n, and then we are going to have various powers of a and b, mixed powers, so that the sum, so that if you take the power of a and take the power of b, so if you have a to the I, b to the j, then I plus j, that is the power of I plus the power of j, that is the power of a plus the power of b, should sum to n if you have a plus b to the power of n. And you have various coefficients. So you can think of, and you have various coefficients in this linear combination. So you can think of, if I plus j is n, then j is n minus I. So you can think of these terms as a to the I, b to the n minus I. So you can think of the coefficient as I, indexed by I. So they are going to, and this is summed over the variable I. So we know that if you expand a plus b whole to the power of n, like we have here, you are going to have linear combinations of terms like this. The question is, what are the coefficients? Okay, once we figure out the coefficients, then we can write down a full expression, which will be a generalization of the simple expansion of a plus b whole square. So how do we do that? So for that, we have the binomial theorem, which can be stated as this, and you notice that the coefficient exactly involves the n choose k quantity which we have encountered earlier in today's lecture. So basically Ci is n choose I. Okay. So how do we do that? So let's take a simple example for warm up. So this is a plus b whole square. So of course we know that a square plus 2ab plus b square is the answer, but let's try to sort of reason about it, why that should be the case. So let's write a plus b whole square as a plus b times a plus b. So now when you expand this, expand the brackets and do the multiplication, then how do you get the terms? Let's try to think of the mechanism of how you get the terms. Well, when you multiply this out, you choose one term from this bracket and another term from that bracket and multiply them. Okay, so that's what you do. So let's trace how we got the various terms in this expansion. So when you choose one term from this bracket, you could choose a. When you choose one term from this bracket, you could also choose a. So that gives you a times a, so that gives you a square. You could choose both b's from here and here, from both the brackets, b times b will give you b square. Or you could choose a from here and b from there, which will give you a times b. Or you could choose b from here and a from there, which will also give you a times b. So that is why you have two appearances of a times b. Okay. So now let's go to the general n case. So you write a plus b whole to the n as a plus b times a plus b times da 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 n times a plus b. So, n times. Okay. So, how do you now get the general term? So, now if you multiply out all these brackets, how do you get the general term? So, what will be the typical term look like? The typical term will look like product of factors chosen from each of these brackets. And these factors, so there are total n factors, either A or B, chosen from each bracket, because there are total n brackets. So, this explains why, and some of these factors will be A's. So, if suppose there are k A's, so from k of these brackets you choose A's. So, from the remaining n minus k brackets you will choose B's. Okay? So, when you multiply these k A's and n minus k B's, you get exactly A to the k, B to the n minus k, which is what you have here. So, now we have to decide what is the coefficient of A to the k, B to the n minus k, because as we saw in the A plus B whole square example, a particular term A to the k, B to the n minus k could appear in many ways by choosing the A's and B's from in many different ways from the different brackets. Okay? So, now let us try to see, if you expand out this multiplication, then how many times does A to the k and B to the n minus k occur. Okay? So, this is actually a simple problem, because you are getting the A's from certain brackets and B's from the remaining brackets, right. So, all that you need to specify is which brackets do you get your A's from. That will automatically imply that from the other brackets you are getting B's. So, you have n brackets in total, each containing A plus B, out of which you want to choose k brackets from which you are going to take A for multiplying out. And from the remaining n minus k brackets, you are going to choose B. So, now it is a simple problem. There are n brackets, you want to choose k of those brackets for picking A. How many ways are there of choosing n choosing k objects out of n objects? That is, n choose k. So, the total number of ways of expanding this into a term, so that you have k A's and n minus k B's, which will give you A to the k and B to the times B to the n minus k, is the total number of ways of choosing k brackets for your A's out of n brackets in total, and that is n choose k. So, you get this expansion. So, although it is general n and it looks complicated, the underlying logic is really simple. Okay. So, you can think of this in terms of what is known as the Pascal's triangle, and the numbers in the nth row are exactly the coefficients in the expansion of A plus B to the n. These are also known as binomial coefficients. Now, observe that the number in each cell is the sum of the numbers in the two adjoining cells in the line above. So, for example, if you look at this sector, 35 is the sum of 20 and 15. So, every number is a sum of two numbers immediately above. So, if you think of this as the n plus 1th row, and this is k, if you enumerate these numbers properly, you will see that this number is going to be n plus 1 choose k, this number is going to be n choose k, and this number is going to be n choose k minus 1. Okay. So, in other words, this simple pictorial representation of the coefficient, so this is, so as you go down the power of n. So, n increases this way, okay, and you get the increasing k this way, k ranges between 0 and n, okay, and you list the binomial coefficients. So, anyway, even if you forget the picture about the Pascal's triangle, it is reasonable to consider, motivated by the Pascal's triangle, it is reasonable to consider this kind of identity involving binomial coefficients, and we will observe, we will use a simple counting argument to prove this equation, prove this identity. So how do we do that? That's another example of a counting argument, and in the next slide we will come to a non-counting argument also. So we will prove this equality or prove this identity. We will see why this equality or why this identity is true in two different ways, one involving a counting trick and the other involving simple algebra and formulas. Okay? So both methods are powerful. Which is particularly useful depends on the context. So let's first look at the counting argument, and it's really neat. You do not have to do an iota of calculation. Okay? So let's think of n plus 1 choose k. So what is n plus 1 choose k? So suppose you are there with n of your friends. Okay? So there are total n plus 1 people, and you want to form a subgroup of size k from here. So how many ways of doing that are there? Well, you are choosing k people ultimately out of n plus 1 people in total. So that's n plus 1 choose k. Okay? Left hand side, left hand side. Okay? So let's now count the total number of subgroups of size k from this total group of n plus 1 people in another way. You see, this group of n plus 1 people contains you and n of your friends. Okay? So when you form this subgroup of size k, the subgroup could contain you, it might not contain you. So suppose this subgroup does not contain you. So if the subgroup of size k does not contain you, then all these k people must be chosen from your friends, and there are n friends in total. So you choose, in the case that subgroup is without you, the number of ways of choosing the subgroup of size k is n choose k, because you have to find all the k people from your n friends. Okay? So now let's look at the other possibility, which is the subgroup contains you. Well, if the subgroup of size k contains you, then one spot in that subgroup of k is already filled by you. So there are k minus 1 spots left in that subgroup, and these k minus 1 spots have to be filled by choosing people from your n friends. So there, for subgroups with you, you choose the remaining k minus 1 members of the subgroup from your n friends, which is n choose k minus 1. And these are precisely the two possibilities of subgroups of size k chosen from the total n plus 1 people. It might contain you, it might not contain you, and basically you count the two kinds of subgroups and add them. Okay? So of course, but this is just another way of counting the total number of subgroups of size k, which you can form out of n plus 1 people in total, and therefore this should equal to n plus 1 choose k, which you had on the left side. Okay? Any questions? Okay. The alternative proof is using algebra. So what you do is that you know formulas for n choose k and n choose k minus 1 and n plus 1 choose k in terms of factorials. So you write them down and play around with factorials using the definition of factorials and do some simple algebra, and you will get it. But this does not involve, it's kind of involving calculation, and it does not give you as much insight as the counting argument gives. Any question? Okay. So let's count the size of the power set. So what is a set? So a set is just a collection of some elements. So let's say a group of people. What is a power set? The power set is the set of all subsets. So in other words, let's take a group of friends like all the students present in this class. So the power set of this set is going to be all possible subgroups of students you can form from all the students present in this class. Okay? And this also includes the empty subgroup which is no student selected. So that's also formally that's also counted as a subset. Okay. So if the size of the class is n, if the size of the original set is n, how big is the power set of n? So what is how many subsets can you form out of a set whose total size is n? Okay. So let's think of this problem. So you can, if you want to count the total number of subsets of a particular set, then so for every subset there is one simple parameter you can look at, which is the size of that subset, and this size can vary anywhere between 0 and n, because you are looking at subsets of a set of size n. So in order to count the total number of subsets of a set X, you can just count how many subsets there are of size k, how many subsets of size 0 are there, how many subsets of size 1 are there, 2, 3, 4, etc., and add those numbers up. Okay? You are just classifying the subsets by their size, counting how many subsets of a particular size are there, and then adding up these numbers. Okay? But now we are in good shape and familiar territory. Why? Because we know that if you have a set of size n and you want to pick k elements, k objects out of those, then the number of ways you can do that is n choose k. So the total number of subsets of size k taken from a set of size n is n choose k. Okay? So the total size of the power set of X, which is the total number of subsets of X which you can form, is just the sum of the binomial coefficients n choose k, where k varies between 0 and n. Okay? And now we will calculate this sum in a simple way. How? Because we know that a plus b whole to the power of n is summation k is equal to 0 to n choose k, a to the k, b to the n minus k. So now what you do is that you simply put a equal to b equal to 1 in this formula. So what you get on the right hand side is that each term, if you put a equal to b equal to 1, this will turn into 1. So you just get summation of n choose k, k between 0 and n, which is exactly what you have here. And on the left hand side, if you put a equal to b equal to 1, you just get 1 plus 1, which is 2. So you get 2 to the power of n. So the sum of all the binomial coefficients between 0 and n is 2 to the n. And that's the size of the power set of X. So that's the total number of subsets of a set of size n that you can form. It's 2 to the n. Okay? Any questions? Okay. So let's do some simple examples involving a rectangular grid. So suppose you have a rectangular grid like the blocks of some cities. So for example, in Manhattan, for example, many of the streets are on this kind of a rectangular grid, and even in fact some streets do not have actual names, they just have numbers. Okay? You can also think of a graph paper. So you have a grid there, and you start from a point A, and you want to go from a point B, and you want to go only either by going east or going north. The rationale is that if you want to go from A or B, you are sort of wasting energy by going backwards or going downwards, right? You have to go up and above, so up and right. So either you take a step, make a step to the right, either you move a block to the right or move a block up, okay? Because you are always wanting to get closer to your destination, which is B. So the question is, how many possible ways of doing this are there, going from A to B by what is called an upright path. So you are always making steps either to the right or up. So here is a possible route, for example. Here is an example. So how do you, so the question is, So the question is, if you know what is A and what is B, how many paths are there? How many such paths are there moving right or up, which takes you from A to B, if you know the identities of A and B. Let's say A is 0, 0 on the graph paper, and B is 6, 3. So let's say A is 0, 0, and B is 6, 3 on the graph paper. Then how many such paths are there? How can you count? So here is a simple example. What you do is that you denote whenever you make a horizontal step, you denote it by 0. Whenever you make a vertical step, you denote it by 1. Okay? So then what happens is that you can represent your path by a string of zeros and ones. The coding is that 0 means a step to the right, and 1 means a step upwards. So you notice that the total number of steps you have to take is 9. So if this is 6, 3. So if you start from 0, 0 and go to 6, 3, you have to take at some point 6 steps to the right and 3 steps at some point up. So the total number of steps you need to take is 9. Okay? 6 plus 3, 9. So that's fine. So the question is, you want to, by representing your path as zeros and ones, you are asking the following question. So you want to arrange zeros or ones, total 9 of them, so that you want to have exactly 6 steps to the right, which is 6 zeros, and 3 steps upwards, which is 3 ones. So you want to find the total number of 0, 1 strings of length 9, so that there are exactly 6 zeros and 3 ones. Okay? So how do you calculate that? Well, you just take the 9 spots and decide where to put the zeros. Automatically the other places you will put 1. So how do you do that? Well, you total 9 spots, you want to choose 6 for your zeros, you do that in 9 choose ways, and that's 9 factorial over 6 factorial times 3 factorial, and you can easily simplify these to get an answer. So let's take another example. So you are starting from 0, 0, and you want to go to 8, 8, and you have the additional restriction that you have to pass through 3, 3 or 5, 5. So these are all on the straight line. Okay? So you want to go from here to there, and you either want to pass through this point or through that point. Okay? So how do you do that? So let A denote the roots from 0, 0 to 8, 8, which pass through 3, 3, so pass through here. Let B denote the set of roots from 0, 0 to 8, 8, which pass through 5. Okay, 5, 5. So the goal is to compute. So you want your path to either go through 3, 3, that is, either it should belong to A, belong to the set A, or it should go through 5, 5, which means that it should belong to the set B. So either B or A, which is A union B. Okay? And you want to find the total number of elements, total number of paths, which either satisfy the condition of A or satisfy the condition of B. Okay? So in other words, if you can look at the set of paths which are in the set A union B and compute its size. So how do you do that? And this brings us to an important principle, which is the inclusion-exclusion principle. So INX means inclusion-exclusion. Inclusion-exclusion principle, what does it mean? Well, it means the following, that if your set A is this one. And if your set B is the other one, which is okay. So then A union B is all the possibilities in the shaded region, and you can write the size of A union B. So you can think of it in terms of this picture, you can think of it as the area of the shaded region. You can write the area of the shaded region as the area of A, which is this, plus the area of B, which is that. But notice that in summing the areas of A and B, you have counted twice the area which lies in the intersection, once for A and once for B. So now you want to subtract the area of the intersection, which is A intersection B, and that should give you the total shaded area, which is the area of A union B. Okay? So that's the idea. So you want to compute this. So using the inclusion exclusion principle, which is using this formula, you can reduce yourself to counting the number of paths, counting the size of A, which is the number of paths from 0, 0 to 8, 8 that pass through 3, 3. The size of B, which is the number of paths from 0, 0 to 8, 8, which pass through 5, 5, minus the intersection, which is the number of paths from 0, 0 to 8, 8, which passes through both 3, 3 and 5, 5. Okay? So these three ingredients we will compute. So let's first compute the number of paths from 0, 0 to 8, 8, which pass through 3, 3. Well, if you want to pass through 3, 3, you have to first go from 0, 0 to 3, 3, and then go from 3, 3 to 8, 8. Okay? So using the logic of the previous example, you take the total distance, choose the number of zeros, the number of horizontal steps. So the total distance from 0, 0 to 3, 3 is 3 plus 3, which is 6. And the number of horizontal steps has to be 3, which is 3. So it should be 6, choose 3. From 3, 3 to, so from 3, 3 to 8, 8, the difference is 5 horizontal steps and 5 vertical steps. So these paths from 3, 3 to 8, 8, there are total 10 steps, out of which 5 has to be horizontal. So it's 10 choose 5. Okay? So it's 6 choose 3 for going from 0, 0 to 3, 3, and 6 choose 3 for 0, 0 to 3, 3, and 10 choose 5 for 3, 3 to 8, 8. Okay? Similarly, for paths from 0, 0 to 8, 8 passing through 5, 5, you have 10 choose 5 for going from 0 to 5, and 6 choose 3 for going from 5 to 8. And finally, the only remaining one is A intersection which satisfies both conditions of A and B. So your path should start from 0, go to 3, then go to 5, and then reach 8. And how many are there? It's the same principle. First you reach from 0 to 3, then from 3 to 5, and then finally from 5 to 8. And then you just use this diagram and this inclusion exclusion principle to calculate. Okay? The inclusion exclusion principle is an important principle, so it has many uses. So this one is a simple example. Okay? Any questions? Okay, so if there are no questions, let's call it a day today, and we will continue next week.